You ever come across a problem that looks, super simple on the surface, but underneath it's just this beautiful, complex dance of physics? Well, we're going to dive into one just like that. It's a famous puzzle from a legendary physics textbook, Problem 1.12, and trust me, it has stumped and inspired students for decades.
All right, so here's the setup. And it starts out easy enough, right? Just picture an equilateral triangle. You've got 3 points, let's call them particles, sitting at each corner. The side of the triangle has a length we'll call A. Okay, now, at the exact same moment, they all start moving. And they're all moving at the same constant speed, which we'll call V. So far, so good, right? But this is where it gets interesting.
Okay, the real core of this puzzle, the thing that makes it tricky, is this one phrase: heading continually for. See, this isn't some simple dash in a straight line to a point that's just sitting there. No way! This is a chase. Particle 1 is always adjusting its path to aim straight for Particle 2. But Particle 2 is moving too, aiming for Particle 3, who's aiming right back at Particle 1. It's this perpetual, totally symmetrical pursuit. So, the big question is, with this constant chase going on, do they ever actually meet? And if they do, how long does it take? I mean, think about it. They're all moving, all chasing, all spiraling in towards the middle. What do you think? What factors are going to determine the answer?
But before we even think about the solution, you gotta know where this problem comes from. This isn't just some random brain taser from the internet. Nope. It's from a book that is famous, or maybe infamous, among physics students all over the world. So yeah, before we crack it, let's talk about the source.
So the book is called Problems in General Physics by the Soviet physicist I.E. Irodov. And let me tell you, this thing is a beast. It's meant for college undergrads, and it's packed with nearly 2,000 problems. And it covers the whole shebang: mechanics, thermodynamics, electrodynamics, you name it. Oh, and get this, the book gives you the answers for every single one. Okay, so we've got this super elegant problem from a notoriously difficult book. Let's get back to the puzzle itself and really break down why your first gut instinct on how to solve it is probably wrong. And this really lays it all out. On the one hand, the setup is just textbook simple, right? An equilateral triangle, a constant speed, a side length. Easy. But the catch, the real catch, is the chase itself. Their speed is constant, sure, but their velocity, that's always changing direction. So they aren't moving in straight lines at all. They're actually carving out these curved paths, spiraling in towards the center. And that's what makes a simple distance equals rate times time formula just not going to work here.
You know, this complexity is totally intentional. Irodov wasn't just trying to test if you could crunch numbers. No, he was trying to build a certain way of thinking. So you gotta ask, what was his whole philosophy here? How did he want students to even begin to tackle a problem where everything is constantly moving? Well, luckily for us, Irodov actually gives us some major hints right there in the book. He basically lays out his strategy. First, he says, really understand what's being asked and draw a picture. Second, and this one is absolutely crucial, solve the problem in its general form. Use letters like A and V, don't plug in any numbers. And third, always check your work to make sure the units, what physicists call dimensions, actually make sense. That right there, that's the toolkit for how to think like a physicist. So, following that advice, physicists and students have come up with a few different ways to solve this thing. Some use clever tricks with relative velocity, others dive deep into calculus with polar coordinates. The point is, the path to the solution can get pretty complex. But the real beauty of this problem is that the answer itself is just remarkably simple. All right, so after all that, after thinking about the spiraling paths, the constantly changing velocities, this whole complex dance between the 3 points, what is the answer? How long does it actually take for them to meet in the middle? And there it is. The time t is just 2 times a divided by 3 times v. That's it. It is just stunningly clean. All that complexity of the chase, all that calculus and spiraling motion, it all boils down to this one incredibly straightforward relationship. So just to quickly recap the variables here, t is the time we were trying to find, a is the starting side length of that triangle, and v is the constant speed of each point. Simple, direct, just elegant. Okay, so we've got the answer. But with a problem like this one, the answer is, well, it's really only half the story. The real goal of a puzzle like this one, like Irodov's three-body pursuit, is the lesson it teaches you about physics itself.
And Irodov himself tells us exactly why he wants us to solve things with letters, not numbers. I mean, he says it right there in the hints. It's all about making the relationship between what you're looking for and what you're given crystal clear. Yeah, getting a number is one thing, but understanding why the time gets longer if the triangle is bigger or shorter if the points move faster, that's the real prize.
And that is the ultimate takeaway here. This problem, and all the other thousands of problems in that book, they're basically training exercises for your brain. They're designed to teach you to look at some complicated, messy, dynamic system and find the simple, beautiful underlying principles that are running the whole show. And really, that's the heart of physics. So I'll leave you with this final thought. The book gives you the answer. We gave you the answer. But the journey to get that answer, the process of actually proving it, that's where the real learning happens. So the question for you is, could you take what we've talked about and find your own way to that elegant solution? Because in physics, sometimes the path is the puzzle.